Welcome to part 2 of the voiceover lecture for Chapter 8, The Special Senses. Previously, we discussed Section 1, Gustation, and Section 2, Olfaction. In this video, we'll continue with Section 3 on Hearing and Section 4 on Equilibrium. In a subsequent video, we'll cover Vision. Section 3, Hearing. What is hearing? Hearing is the ability to perceive sounds, like the major scale that I just played. Sound is a vibration that propagates as a wave through a medium. Sounds can propagate through solids, liquids, or gas, like the air that we hear most sounds through. Deafness is defined as the significant or total loss of hearing. Now let's discuss the anatomy of the ear. The ear is divided into three main regions. The outer or external ear. Its role is to funnel sounds into the ear. The middle ear transmits sounds to the inner ear, and finally the inner ear converts sound to neuronal signaling that will travel to our brain where we will perceive sound. There are three parts of the outer ear that I'd like you to know. The auricle, this is the most obvious part of our ear. It's the flap of cartilage covered by skin. It funnels sounds into the next part. The auricle is also known as the pinna in other animals. So the auricle funnels sounds into the external auditory canal. It's a tiny passage that travels through the temporal bone of our skull. The external auditory canal is about 1 inch long. We know our skull is not 1 inch thick, so the external auditory canal does travel at a slight angle into our skull, making it a little longer. And thirdly, the tympanic membrane, also known as the eardrum, is a thin membrane and it vibrates due to sound waves. The tympanic membrane divides the outer and middle ear. In this diagram, you can see the anatomy of the ear. The auricle is this structure here, what most people think of as the ear. And the external auditory canal is this channel right here. The outer ear ends in the tympanic membrane or eardrum, located here. We'll come back to these other structures when we explore the middle and inner ear. Next is the middle ear. The middle ear is an air-filled cavity within the temporal bone of the skull. Within the middle ear are two major parts to know. First is the auditory ossicles. The auditory ossicles are a collection of three small bones. In fact, these are the smallest bones in the human body. First is the malleus, then the incus, and then the stapes. The malleus is attached to the tympanic membrane and will vibrate as sound waves vibrate the tympanic membrane. The malleus's job is to transfer those vibrations to the incus. The incus is in the middle, it's between the other two ossicles. So it will transfer its vibrations to the third bone, the stapes. And the stapes fits into the cochlea and will transfer sound waves into the cochlea. We'll talk about this process later on. The second major part of the middle ear to know is the auditory tube. It's also known as the eustachian tube or the pharyngotympanic tube. I'll just have you know it as the auditory tube. The auditory tube is a small tube that connects your middle ear with your nasopharynx. That's the region where your nasal cavity meets your throat. The auditory tube allows air in and out of your middle ear. It does this in order to equalize pressure. The equalization of pressure within the middle ear gives that popping sensation. If you've ever traveled in an airplane or driven in a car up a hill, you might notice your ears popping. As you travel up in elevation, the atmosphere has less pressure, and we want that pressure in your ear to be released to equalize with the surrounding atmosphere. The air has to travel through the auditory tube into your nasopharynx. We don't want air traveling through the eardrum because that could rupture it. Here's a diagram showing the anatomy of the middle ear. You can see here is still part of the outer ear, the external auditory canal, and the tympanic membrane. But this chamber here is the middle ear. Remember, it's filled with air. Within the middle ear are the auditory ossicles, which include the malleus, incus, and stapes. Also in the middle ear is the auditory tube. So this tube would travel down and to the nasopharynx. Finally is the inner ear, also known as the labyrinth. The inner ear is a complicated series of canals. In regards to hearing, there's one major structure of the inner ear I'd like you to know. That's the cochlea. The cochlea is a small, bony, snail shell-shaped spiral canal. The cochlea is filled with a fluid known as perilymph, and it also contains special sound receptors called auditory hairs, also known as hair cells sometimes. Those auditory hairs have tiny projections called stereocilia. Stereocilia will bend in response to sound waves. The bending of the stereocilia will cause signals to be sent to neurons, and those signals will travel to our brain. This diagram shows the structure of the inner ear. The inner ear has several parts, but in regards to hearing, I would just like you to know the cochlea, this spiral-shaped canal. The stapes fits into the cochlea, and we'll see how that works in later slides. Here's a cross-section of one of the canals of the cochlea. You don't need to know all of these various structures. The most important part is this middle region here. There's a membrane, and within this membrane are the hair cells or auditory receptors. Now let's discuss the physiology of hearing. Sound waves will hit the tympanic membrane and cause it to vibrate. The vibration of the tympanic membrane is transferred to the auditory ossicles. That's the malleus, incus, and stapes. The third auditory ossicle, the stapes, is connected to the cochlea through the oval window. The oval window is a hole in the cochlea, and the cochlea is filled with fluid. As the stapes moves in and out of the oval window, it vibrates the fluids within the cochlea. This creates sound waves in the fluid in the inner ear. As those sound waves travel through the spiral-shaped cochlea, they bend stereocilia. This animation demonstrates how sound waves travel through the ear. To the far right, it's hard to see, but sound waves are traveling through the external auditory canal and hitting the tympanic membrane. The tympanic membrane vibrates in response. That in turn vibrates the malleus, which vibrates the incus, which vibrates the stapes. Notice the stirrup shape of the stapes. The stapes is fitted into the oval window of the cochlea. As the stapes vibrates, it moves in and out of the oval window. The cochlea is filled with fluid, and as the stapes vibrates, it will cause vibrations or sound waves in the fluid of the cochlea. You can see these sound waves traveling through the different chambers within the cochlear canals. As those sound waves travel through the cochlea, they put pressure on and bend stereocilia, which are located on the auditory receptors or hair cells. Section 4, Equilibrium. Equilibrium is the ability to perceive balance, acceleration, and orientation. The organs involved include our eyes, where we can see how we're balanced and how we are moving in space, In this section, we'll focus on the inner ear. The inner ear has hair cells in it, just like we saw for the process of hearing. Just like in hearing, the hair cells have stereocilia. In this case, the stereocilia are embedded in a special gelatinous goo called the otolithic membrane. I'll show you the physiology of this on the next slide. The inner ear is composed of three parts. We've already discussed the cochlea, which is involved in hearing. The other two parts are the vestibule and semicircular canals, which were involved in equilibrium. Let's zoom in on the vestibule and semicircular canals. Within those structures is a epithelial layer which has hair cells embedded in it. Those hair cells have stereocilia that stick up and into a gelatinous membrane known as the otolithic membrane. This goo has little tiny hard calcium carbonate crystals in it that kind of give it some weight. When your head is upright, the membrane sits flat. When you tip your head forward, or when you're accelerating, the gooey membrane is pulled in different directions. You can see here, when you tip your head forward, the force of gravity pulls the otolithic membrane downward. That pulls on the stereocilia, allowing ions to flow into the hair cells, starting an action potential. The same can be said for when we are accelerating. If we move forwards or backwards at an accelerating rate, that will move the otolithic membrane, which will move the stereocilia, and we'll sense that due to the formation or initiation of an action potential. And that's all you really need to know for this class for equilibrium. And that's it for part 2 of the voiceover lecture for Chapter 8.